So what you see are two questions in front of you. One is a triangle, and the other one is a blue sort of triangular-like shape. They both have a base of 3. But since this one on the left is the other side is the line y equals x, this is also 3. But for this one, it's the curve y equals x squared. So this point is over here at 3, 9. Okay, would you take a few minutes to think, what are the approximate or exact area for those two regions? Okay, I see in the comments that yes, the one on the left is a 45, 45, 90 right triangle, and its area, you could actually get the exact area, is 4.5. And yes, Melissa says it's somewhere less than 13.5. Good observation that if I actually joined these 2 points, well, this green triangle would have an area of 13.5. So this blue region is somewhat less than 13.5. But how much less than 13.5? Anyone have any guesses on that? Ethan, I see a hand up. Do you want to say? What do I do? You want to say?
That was an accident. I'm sorry. I really don't know.
Oh, that's all right. You want to take a guess? Anything less than 13.5 is a guess. Okay. Well, that is a question that we will find the answer out, not only to that question, what's the exact area of the triangular region on the right, but other questions related to it. The question, the top question here, oh, and someone asked about Fermat's method. Well, Fermat's method is about the slope of the tangent line. And this one is a question about the area under the curve. It is true that the bigger the slope at a region, sort of the area goes up also, and we'll see the relationship between those two concepts coming up. Now, question 1 is something you probably know from last semester and from last year. What is 1 plus 2 plus 3 plus 4 up to 100? You could type it in. Either you know the formula, yes, it is 50-50. Oh, Fermat's method. You mean Gauss's? I see. Yes. It is 50-50 though. Yes, the formula for 1 plus 2 up to n is n times n plus 1 over 2. that formula is justified really quickly. The first and last number add up to n plus 1, sort of the second and second to last number, and the number of pairs is n over 2. Now, a less known formula is what the sum of the squares of the first n integers is. But that's a formula that we'll need to know the answer to be able to do a question that's coming up. Anyone know, just because they've encountered it, they messed around with it? It's not at all an obvious formula. I'll tell you that it's n times n plus 1 times 2n plus 1 over 6. And there's various ways to prove that formula, but let's keep that formula in our back pocket in case we have an occasion in the next half hour to need to know what the sum of 1 squared plus 2 squared up to n squared is. And why not give you the sum of the cubes? Oh, but by the way, if I type in 100 times 101 times 201 divided by 6, I get 338,350 for this question. And whoops, what happened there? That should be cubes all around. It turns out that the formula for the sum of the cubes of the consecutive integers is the same formula as the sum of the first formula, but the answer then squared. And these formulas, and you might wonder, what about fourth powers and fifth powers? We'll talk about those. Those are important formulas that are they're not obvious formulas, they're hard to derive. Usually you can, if you know the first couple of formulas, there's a way to get the next one from the ones before. But we'll be restricted by the number of these formulas we know at first, and here are 3 of them. Again, keep them in your back pocket for later. This is what I was just talking about. Here they wrote the formula, they actually squared it, so it's n squared, n plus 1 squared over 4, but I like to write it as n times n plus 1 over 2 squared. There's some really nice visual proofs of those. I'll put links up to those. Okay, what do sums of integers and sums of powers have to do with today's lesson? Well, here we have a triangle. And we've known the area of a triangle is 1/2 base times height, which made the area of this triangle 4.5. But now I'm going to show you a much more complicated way of getting that same answer. Now, why do we need a more complicated way? Well, that more complicated way will be more flexible in general for other shapes besides triangles where the third side is a straight line. And here comes the insight. Let me see if I can bring up a different window. Okay, so on your screen here, the concept is, what if I were to make a thing like this, sort of like a staircase? Basically, what if I split up the bottom line into an equal number of segments, in this case 4. And I made it so that we made the rectangles in this way. Let's say I had 6 rectangles. The sum of those rectangles, let's say I don't know the area of a triangle, but I know the area of the rectangles. The sum of those rectangles will be close to the area of the triangle, though it will be slightly bigger. But if I have a method of finding the exact area of something like this, if I have a formula that lets me tell how many rectangles are there, and it tells me what the sum of the areas of all those rectangles are. Well, if I can somehow make those rectangles an infinite number of them, I can get the exact answer to that question. The reason that's going to be useful is because that will also work if my third side of the triangle looking thing is a parabola. Or some other thing, let's say a cubic. So that's going to be the insight. And I'm going to take you through how this works. Let me go back to the iPad. Okay, first I'm going to go real specific. I'm going to say, what if I were to split this thing into 6? I'll say n is the number of rectangles, into 6 rectangles. So I would split this this line segment is 3. So I'd split it 1, 2 into 6 rectangles. And to make it clear, the height of the rightmost rectangle is going to be 3. And this second to last rectangle is going to have a height of 2.5 because the height's always the same as the x coordinate and the y coordinate are the same. So this x coordinate is 2.5. That makes this y coordinate at this point 2.5. And that's going to be the height. So here I have the 6 rectangles. Now, if I want to write what the combined area is, I can say area equals, can someone type in what's the width of each rectangle? That's correct, it's 0.5. And I'm going to write that as 3/6, just so, because I kind of want to see this n equals 6 involved, but I took the full interval and divided it by 6. And the first rectangle also has a height of 3/6, which I'm going to write, if you don't mind, as 3/6 times 1. Now the second rectangle has a base of 3/6. They all did. But what's the height of the second rectangle? You type it in. What is the height of this shaded in rectangle? Hint, it's whatever the y coordinate of that point is. Yes, it's 1, which we could write as 3/6 times 2. Writing it as 1's fine also, but you'll see why I'm going to write it as 3/6 times 2. Remember, these x coordinates on the axis are 3/6, 6/6, 9/6, 12/6, 15/6, 18/6. Now, if I do this all the way down, the last one is going to be 3/6 times 3/6 times 6. And notice how they all have 3/6, 3/6. So I'm going to write that as 3/6 squared. But what's left is 1 plus 2 plus 3 plus 4 plus 5 plus 6. And 1 plus 2 plus 3 plus 4 plus 5 plus 6. Yes, it's 21, but I'm going to write it as 6 times 7/2. Because we have a formula for the sum of the consecutive integers. And if I cancel out this 6 with one of these 6's, and I'll write this as 3 times 3 and cancel this 3 out with this one, I end up with 21 over 4, which is 5¼ Now 5¼ is not the area of the triangle. It's bigger. So this is just an approximation. This is the question we just did. Okay, now what I would like you to do is, could you go through the same process, but now I'm going to do it with 40 rectangles. And the answer is not going to be 4.5, even though 4.5, it's going to be bigger than 4.5, but what is it going to be exactly? I'm going to pause the recording, have you, and I see an answer of 4.6125. Let's take a look. And that is the correct answer. Notice how it became almost the same expression. The only difference was that this number here was not a 6, it was a 40. And this number here was not a 6, it was a 40. And this number here was not a 6, it was a 40. And this was not a 6 and a 7, but a 40 and a 41. Now, you might wonder, can I make n equal to infinity to get the exact answer? Well, we don't have a formula for 1 plus 2 plus 3 plus whatever up to infinity. But what we can do is use our new friend, limit. You see, when it was every term, it ended up turning into this, right, each time. It ended up being 3 over 6 squared or 3 over 40 squared, and then times n plus 1. See, that we can do. See, this formula here would allow me to put any value of n in that I want. I could put 6 in to get the first question. I could put 40 in to get the second question. And no, I can't put infinity in. But I can, because I learned 2 classes ago, actually 3 classes ago, how to answer this question. Does anyone want to say what the answer is? How do you take the limit as n goes to infinity of an expression like this? Imagine if you were to multiply out the numerator and denominator. It might be, or at least you don't actually have to multiply it out, but if you kind of picture, what would you do? What would be the leading term? Because that's all that matters for infinity limits. What would be the leading term for the numerator? If I actually multiply this all out, if I multiply the whole numerator out, what would be the leading term for the numerator? Well, the coefficient would be 9. But the actual full term would have some n's in it. Yes, it would be 9n squared. And yes, there would be other stuff, but that other stuff is never important when you're doing a limit to infinity. You might remember from 3 classes ago. And what's the denominator, at least the leading coefficient of the denominator? It's 2n squared, because this squared here is part of it. And this actually has an answer of 9 over 2, because these powers are the same, so you take the ratio of the coefficients, which is 4.5. And 4.5 is the exact area of that triangle. Well, seems like a lot of work to get the area of a triangle. And just to go one more step further with this, what if instead of calling the rightmost point of this, like the boundary here, what if I just left that as an x? Well, then it would become limit of, as n goes, n is still the number of rectangles, it would be x over n squared times n times n plus 1 over 2. And that would turn into x squared over 2. It would be x squared n squared over 2n squared, but, well, that's even more general. So that tells me that the area of this triangle is x squared over 2. Well, we knew it was going to be x squared over 2. It's just a right triangle, so the area is going to be x squared over 2. Again, that's a lot of work to find the area of a triangle. But we learn it because it enables us to do this question now. Now, this one's a lot harder. I think I'm going to have you work this out for n equals 6, n equals 40. And I'm not going to say n equals infinity. I'm going to say limit as n approaches infinity. This is 3 is the right-hand boundary, so we will use like the specific number 3. That way we'll get an actual answer. Remember, it was less than 13.5, but what is it? Someone asked about the sum of infinite numbers could be negative. Yeah, that's Euler with geometric series where the terms are getting bigger than each other. Okay, I'm going to put you now, write down these questions because I'm going to put you into breakout rooms to talk about these 3 questions. And I know the screen gets turned off when you do that. Okay, I'll put you into the breakout rooms now. Let's see how this works. Here, I'll pause the recording. Okay, recording resumed. Our answers for the first one become about 11.375. This used the, sum of the squares formula got used. Sorry, I had paused the video. There is a second video up that shows more of the details of this if you're watching this and you weren't at the live class. Anyway, when you make the limit as n goes to infinity, you get 9. So remember in the beginning, we knew it was going to be less than 13.5. Well, it turns out that the exact answer is 9. We know that the width is 3 over n because 3 was the entire, 3 was the length, this length here, or on this picture, 3 was this length. But since I was cutting it up now, not into 6 or 40, but into what I was calling n different rectangles, each width would be 3 divided by whatever that n is. Now, if I want to get even more general and just call this x and still let n go to infinity, it would turn into x over n cubed times n plus 1 times 2n plus 1 over 6. This here is the 1 squared plus 2 squared plus n squared that would come up eventually. And this here is the x over n was the width, but there was also an x over n squared that got factored out. And when you put this all in, when I do the limit, not as x goes to infinity, but as n goes to infinity, you end up with 2x cubed, n cubed, plus a bunch of other stuff on top. The denominator becomes 6n cubed. And it reduces to x cubed over 3. At this point, we might generalize. If it was y equals x, the area became x squared over 2. And when it was y equals x squared, the area became x cubed over 3. Does someone want to speculate what the answer would be if it was y equals x cubed as my curve? And that's right, it's x to the 4th over 4. Now, for this one, what would be needed to actually do, what's going to end up happening if you're actually going to do the x cubed case? What do you suspect you're going to need at some point? What are we going to need when we break this up into rectangles again? What's going to end up happening, do you suspect? No suspicion, considering that the one with x, that this one required at some point the sum of squares. And the original example, the triangle one, that one involved just the sum of integers. And yes, we're going to need, in order to do this one, we would need the sum of cubes formula. Which was given in the beginning, but beyond that, we're going to need other formulas to prove them. But I think that's good for our purposes now. Now I want to go one last sort of thing to basically end a final big finish of the new material and the end of this course. If I did y equals 2x, the area would get doubled because when every y coordinate gets doubled, the area gets doubled also. So the area would be x squared. And if I did y equals 3x squared, the area would be x cubed. And if I did y equals 4x cubed, the area would be x to the 4th. Okay, do you notice anything that related to yesterday's lesson or for whatever the last lesson we had? Anything where these expressions were related to each other? When was there a situation where we started with x squared in a problem and the answer ended up being 2x? Okay, I see Willis says derivative, which is the official word, but slope was what I was calling it at the last lesson. You remember a few days ago when I asked what's the slope of the, what's the slope for y equals x squared, and the slope was 2x. And the slope of the tangent line when y is equal to 3x, when y was equal to x cubed, turned into 3x squared. So here are two concepts that seem totally different from each other. The concept of finding the area underneath the curve and the idea of finding the slope of the tangent line of a curve? Well, the fact that, if you find the area of 2x and it ends up being x squared, and then you find the slope of the tangent line for x squared, it ends up being 2x, that these two concepts, area and slope, are linked together. Oh, some people have to go. So I'll just say that's called in math the fundamental theorem of calculus, that area and slopes are like inverses of each other. And that will be a good last word in this course. I'm going to pause and stop the recording, but some people want to stick around, maybe ask questions.